So we just start within 1 minute. Just wait for 1 minute and then we'll start, okay? Okay, so we are already late, so let us start. So without, can you hear me first? Let me confirm that and see my screen.
Yes, sir.
So welcome to the week 5 of the live interactive session of the NPTEL course Introduction to Electrical Engineering, and now we are in the week 5. So today's week topic will be diode circuits and two-port networks, as I've already told you. And if you have not joined the group, you can just join the WhatsApp group so that we can discuss some doubts if you have. So I guess all of you by this time will have the WhatsApp group link, and if not, I can share also with you. So there you can post your doubts and get those doubts clarified also. So just let me share the WhatsApp group link. So there you can just join and just post your doubts if you have any doubts. And you can also join this live session 5 or 10 minutes before and ask your doubts. Nobody is asking doubts, but asking doubts is very much advisable because you are all in the learning phase, and if you don't practice and don't ask your doubts, that those will remain forever. So these sessions are actually designed to be interactive for you to join and then practice mainly. So I shared the WhatsApp group link so that you can join and get your doubts clarified. I hope that will help. So without wasting much time, let us just start the session. Before that, you can just confirm whether you can see my screen or not and my slides moving, right?
Yes, sir.
So just about the sessions, because if some of you are just for the first time, so we held these sessions every Tuesday, 7 p.m. to 9 p.m. and there will be 13 such sessions, right? Every week we discuss the weekly concepts and solve the problems, and then there will be a final session where we will review and maybe revise all the concepts and solve some important problems. So we are at the week 5, and I hope you don't have any doubts, because by this time I would have got many doubts, but I did not get any doubts. So if you have some doubts, kindly let me know. And some concepts, if you want to just discuss those concepts again. So just I want to confirm if you have any doubts from the previous weeks or this week also. Otherwise, we'll just move into the content of this week and just start the session, right? So kindly let me know if you have any doubts, or else I will go ahead. Yes. Any doubts? So no, I guess, right? Because none of you are responding. And please be interactive because these sessions are meant to be interactive and for practice. So keep a pen and paper with you. It is very much advisable and solve with me. And anywhere you get any doubt, just stop me and ask the doubts. That is actually the whole point of these sessions, right? So if you are in the session, it is advisable that you are with a pen and paper and practice because these sessions are meant to be interactive. So you should interact, right? I hope my voice is also audible and everything is going smoothly. So just coming to the weekly content, we are in the week 5 as you can understand, and we are going to discuss diode based circuits and two port networks in this week. So first I will deal with diode based circuits, right? And then we'll move on to two port networks, how to deal with such problems. So as you know, diode based circuits, let us discuss how those can be implemented and various type of diode based circuits. Let us see how many types of diode based circuits are there and what are their operations, right? So the first kind of circuit that is used is the half bridge rectifier. So what the diode is used? Diode, do you know? Are you comfortable? What is a diode? Can anyone tell me? Diode is a it is an electronic device, right? So what it does? Yes, you can just unmute and just speak.
Diode is a semiconductor device.
Correct. So what it does? It
The
blocks the voltage.
current flows in one direction.
So that means it what it does?
Current
It
flow in
blocks
one direction.
correct, and also it blocks the voltage, reverse voltage, right?
Yes.
So maybe if you impress kind of voltage, opposite polarity voltage, like we denote the diode like this, and this is the positive and this is the negative part, we call it. And if you impress opposite polarity voltages, it will block it. Block it means it will behave like a switch, right? A kind of uncontrolled switch, which is not in your hand. It will be dependent on how the voltage polarity is. So if the voltage polarity is positive, the diode will just behave as pass through with some small drop, maybe zero point 0.7 volt or something. If the voltage polarity is positive. So positive voltage is a necessary criteria for the diode to conduct. The voltage across diode should be positive for the diode to be forward biased. So we call it forward biased, right? And obviously, as you told, the current should be also in the entering the through the positive terminal like this. Then only the diode will conduct. So two criteria. So and obviously, if it is reverse polarity voltage or current in opposite direction, it will just not allow the flow of current, and we tell it to be reverse bias condition, right? Reverse bias negative voltage, right? So there no current flows, and here current can flow. So with this small knowledge, because we are seeing it from the electrical perspective, not in an analog engineer's perspective, so we are only operating in the cutoff mode, right? So obviously diode will behave like a switch here, and no, we are not operating in any other zones, and the diode is only seen as an electrical switch here with some drop. So just can you tell me what will happen if I impress AC voltage across the diode in the positive half cycle? What will happen? The voltage at this side, if it is greater than the voltage on this side, or in other words, you can tell if the voltage polarity is positive at this terminal, so then the diode will just pass the voltage here. Yes. So what I am telling, if the voltage, input voltage is like this, you only need to take the positive part. Then the voltage across load, if I see this voltage VL, voltage across load, how will it look with time? Only the positive part will be passed. Because when the diode will be shorted or when the diode will actually connect the input to the output, then only the voltage will appear, right? Okay, so then only the voltage will appear across the load. In other words, if the diode is reverse biased when in the negative half cycle, because you see that when the voltage becomes negative, then the diode will be off, and then what will happen? It is simply 0 volts, right? And this will only appear here because no current will flow. So this is kind of waveform that will happen in every cycle. The positive lobe will only. So this kind of waveform we'll call it half wave DC voltage, right? But we actually don't prefer in the rectifier which will support the load, the voltage across the load is discontinuous. So it is not preferable actually. So we move on to the next part, advanced version of this circuit, right? Which you have the AC source and then a transformer to either step up or step down as per your requirement, because the load may be having some voltage rating. So because the supply line is 220 volts, but if you want to only glow a LED, small LED, then it is having smaller voltage capability, right? Or rating. So you step down maybe 10 is to 1, so 22, or 100 is to 1 also, 2 volts. Then what will happen? These 2 volts we can split in 2 parts. So one part, this part, if you assume as the reference, then the voltage at the upper part is more or higher than, because as you go upward the voltage is increasing. So this part voltage is actually higher than the reference. So reference is actually assumed to be 0 volt, and this is 220 volts. So how much will be 2.2 by 2? So at the this side, V secondary I can write is 2.2 volts. But this, how much is this voltage? This much, because this reference point is splitting the voltage at the secondary in two parts, two equal parts. One part is 1.1 volts. So this part is, this node is at 1.1 volts, and this node is at minus 1.1 volts. So that is what the difference between the top and bottom part, and the secondary voltage is coming 2.2 volts. Then this voltage is like this. When this voltage 1.1 volts means it is AC voltage, right? Like this, RMS. When this is the top voltage, then the bottom point voltage will be just 180-degree phase shifted. When this lobe is positive, this lobe will be negative, like this, because this is plus 1.1 volt and this is minus 1.1 volt. So voltage will just 180-degree shifted, or in other words opposite. So you see this part, then what will happen? This diode will conduct because the voltage diode conducts in the positive lobe. Then if you write it as D1 and D2, then D1 conducts in this part, D1 conducts in this part, D2 conducts. Then how will the waveform look like? Waveform and across the load will be how? If this is the waveform and this is the waveform of the bottom part, then in this part, in the first part, the D1 will bring the plus 1.1 V sine omega t or whatever you call across the load. So voltage will look like this. But in the next half, this minus 1.1 V sine omega t will become positive, as you can see. And the plus 1.1 volt sine omega t will bring the negative. So in this half, D2 will conduct. So here D1 conducts. Here D2 will conduct. And when D2 conducts, then it impresses what kind of voltage at this point? Same, positive voltage. So it is kind of full wave voltage, right? With some ripple. With ripple, right? Because we are not using any capacitor or voltage filter across the load at the output. So this is also one kind of solution to get a DC voltage at the output, continuous DC voltage, but with some ripple at the output across the load. But as you can understand, there is a transformer sitting here. So this transformer is bulky, right? So that is a problem which first of all it increases the cost, and it increases the also space and weight. So these kind of circuits are not very much portable, because DC circuits are powering a load which is very small, requires a small portable device, as you can understand. So that is not very much convenient to drive these kind of small loads or small application. So, but this is also one application. So can you tell me, when D2 is off, what is the voltage across it? What voltage is it blocking? Can you tell me? When D2 is off, what voltage is it blocking? Please understand, when D2 is off, for sure D1 is on. So when D1 is on, you can just replace it with a short as an ideal device. So what is the voltage across D2? If you draw the diagram, then you can understand. You have a secondary like this and a reference point, and then you have, one second. Yes, then you have D2, right? D2 will be reverse biased. So you can, reverse biased means you can open, and D1 will be forward biased. And then you have the load. This is the both are the reference points. So that means the load is actually connected here, right? You can also write like this. So is, instead of representing like this, I can also, and then you have the load. This is the both are the reference points. So that means the load is actually connected here, right? You can also write like this. So is, instead of representing like this, I can also, I told you this point is the reference point, so 0 volt. So if this is 0 volt, this will be plus 1.1 volt RMS AC. And if this is plus, I told you this point is the reference point, so 0 volt. So if this is 0 volt, this will be plus 1.1 volt RMS AC. And if this is plus, then this should be minus 1.1 volt RMS AC. This means that the both the waveforms are 180-degree phase shifted, should be, because otherwise you will not get the voltage difference del V secondary to be 2.2 volts, because it was 220 volt and 100:1 means 2.2 volt should be there. So that's how we did it, because it is a center tap. So we did the midpoint to be the reference point, and then accordingly the top voltage is 1.1 V sin omega t, and then the bottom one is minus 1.1, or other words, the phase inversion. So if that is true, and the one cycle we consider that D1 is forward biased, then I asked you what is the voltage across the second one, the D2. Can you tell me by KVL? Just apply KVL. This is 0 volts. This is 1.1 volts. So the voltage here is 1.1 volts. And the voltage here at this point is minus 1.1 volts. So what is the voltage across the diode? Del V diode is nothing but 2 times this voltage, Vm RMS or Vm RMS. Both are equal in amplitude, right? So because the peak inverse voltage, we tell it, that is the voltage, maximum voltage that the diode will block, is 2 times Vm peak. Because peak voltage amplitude wise, so 2 times that, right? Because it is, we can see 1.1 minus minus 1.1, so it is becoming 2 times Vm RMS. But if someone asks you, this is the RMS blocking, but if someone asks you the peak inverse voltage blocked, then you will replace by RMS into root 2, and nothing but peak. So this is the peak voltage, 2 times peak voltage. So remember, in a center tap configuration, what happens? Peak inverse voltage equal to, that is the maximum voltage that the diode circuit will block, is nothing but 2 times V peak. Right? Clear? Any
Yes,
doubt?
sir.
Yes. So 2 times V peak, it will be the maximum blocking voltage that the diode will incur. So accordingly, you have to choose the two devices. Both the two devices that you will be using in the diode-based circuit in a center tap configuration should be rated at least 2 times the maximum supply voltage. This supply voltage. Sorry, this secondary voltage. V secondary, right? Basically, it is dependent on supply voltage only, because you choose the supply voltage such that the V secondary is a kind such that its peak times 2 is the rating of the diode. So indirectly, it is obviously related to the supply rating, because the supply rating will decide the peak voltage at the secondary, and the peak voltage at the secondary will decide the rating for the diodes. So all are interlinked, right? So that is how you choose the rating for the devices to be used or to design the center tap rectifier. Okay. Any doubt in understanding this? Why 2 times? Because sometimes you have confusion, because this is AC. Please understand, this is not DC. So you have to always think in terms of both amplitude and phase. Okay. And all we are dealing with are RMS quantities here. Like I am writing 220 volts. If someone just tells you that your house is getting 220 volt AC supply, they indirectly mean that it is RMS. So when we are not specifying anything, it means RMS voltage I am telling. And obviously, if someone asks you what is the peak, because for devices like diodes and other devices, we have to choose their rating based on the peak, right? Otherwise, they will blow. Because this kind of diode based circuits we are not using for DC, we are using for AC. AC has a peak voltage, right? So accordingly, their device blocking capability or rating, they should be rated actually to block that peak voltage. But here the voltage that it has to block is 2 times that this voltage peak. Okay. So hope you understand what I am trying to tell, right? Or else, in other words, this full secondary voltage the diode has to block. That is also how you can see it. And this full secondary voltage is nothing but 2 times that this part voltage, because they are equally tapped, because the name center tap, right? So equally splitting both the top and bottom parts across the load. So understood, or I need to repeat anything?
Good, sir.
So let us go to the next part. We come to the full bridge. Okay. Why we came to the full bridge instead of using the center tap rectifier? Center tap was also doing full continuous voltage rectification every cycle. It was not discontinuous, unlike the halfway. But still, we went to the full bridge using 4 devices. Instead of 2, we now have 4 devices. Why? Why we went to full bridge? Any motivation? Why 4 devices is preferable? That is, why not center tap? Because action is same, right? Or result is same. Result is equivalent, right? At
Sir,
output. Then why? Why this? Yes, tell. And then we'll dive deeper into the full bridge rectifier, because this is important, right? For the load perspective. Because load likes this kind of voltages, continuous voltages, unlike the half wave. So let us analyze it further. So yes, tell me why so? Why not the center tap, and why we are so much using actually in electronic circuits the full bridge rectifier? It is everywhere. Full bridge rectification is done mostly in every places. Your maybe rectification you are using, and this full voltage action, I can tell, is happening in many places, in drives, in your computer, many places, in your PCs actually. So why? Why 4 devices? Any preliminary motivation you can tell just by seeing the circuit? Okay, we are using 2 more devices instead of 4. In the center tab, we are using horizontal bridge, but still I am telling why. Can you tell me at least one reason? Yes? Any one of you, just feel free to answer, okay? Because the transformer gets eliminated, right? So it becomes very much portable, right? And cheaper. Because iron is costly. Diodes are 1-2 rupee. But generally small rating diodes are available in 1 rupees. So transformer is costly because iron is costly, right? And winding material is too costly, copper. And its design is complicated, its weight is more, it takes a lot of space. So space low,
Sir, I have one
weight
doubt.
low.
Sir, I
Yes,
have.
yes, please.
Sir, in full bridge rectifier, input is around 20 to 30 volts, sir. Hello. Sir,
Tell me.
sir, how to getting sir, if you applying 230 volts single phase AC, these diodes are not withstand, sir.
Mm. Correct. So then in 230 volts,
How
we
to?
don't apply 230 volts. I am
I
telling.
have one doubt, sir.
There are
How to
three.
apply very low voltage to diode input, sir? Diode input. Source voltage is very low. Without
Yeah.
transformer,
So
how to
what will
apply?
to
Without transformer, how
to
to get low AC voltage?
how to get
To get low AC input.
low S? That is what I'm saying. How to basic solution.
Sir,
What
your voice not audible, sir.
am I audible? Hello.
Now okay, sir. Now okay.
One
Sir,
very easy solution is without
now
using transformer. Just plug in this resistance because
okay, sir.
LEDs will not consume very high power, right? So your
Yes.
power dissipation at the resistor will not be that high. So we use actually like this only
Okay.
in the home. To maybe
Decorative lightings.
or tape. There are the god
Sir, your voice
chemical.
not audible, sir.
So there
Your voice not audible,
just
sir.
let me check. Okay, just what is happening? Let me check. Now is it audible? Hello.
Now okay, sir. Now okay.
So what I was telling is that in Mandir or some places we use very glowing LEDs which are of low rating, very low rating and low DC voltage capability. So there we
Yes.
cannot use without transformer as per your doubt. True,
Yes, sir.
transformer is a
Got it, sir.
possibility. In DC
Got it.
eliminator, in robotics when we used to play in the when we were kid in robotics, we used batteries. But what if we want to drive with AC? We had to use a DC eliminator. You remember in the when you were small, you must have used DC eliminator in your school projects. That is one DC eliminator has a transformer where you get 12 volts or 6 volt settings DC and a bridge rectifier. That was one. But how to take a bulky transformer? It is very weighty, right? In every appliances to fit a transformer, it is very costly. So this is a solution provided that the appliance is of very low power rating. I am
Slides
interested of
are not,
electronic circuitry. Yes, electronic
sir,
circuit.
slides not visible, sir. Slides.
Okay. Slide I am presenting. I did not present actually. So you understood, right?
Yes, sir. Understood, sir.
Just wait. Slide is coming. Hope the slide is coming.
Coming, sir. Okay.
So that is I am telling this is a very rough solution in a low power circuitry device. Low DC, low power circuitry device like LEDs or glowing lamp using motors, DC motors. You can use some kind of tacho generator, small tacho generators, very small, like your battery driven generator kind of motors, and then they are glowing some lamps. You understand, right? Toys. So that can be inbuilt. Because what will happen, either ways the motor rotating in forward direction will generate forward AC voltage and kind of commutating action. So this kind of circuitry will produce DC voltage irrespective of the same polarity, as you can understand, irrespective of the polarity on the AC side. That you agree? Irrespective of whether this is this or this, that is inverted or not inverted in respect to time, the voltage in this side will always be like this. That is, this rail will be always negative. This rail will always be positive. Hope you understand what I'm. Sorry, this one I am telling at the load DC side, load DC voltage, right? So this rail will be positive always. This rail will be negative always. Hope you understand what I am telling. Irrespective
Got it,
of
sir.
irrespective of the polarity at the input, these kind of applications are very much suitable to use your low power circuitry in your home appliances. Low
Laptop
DC
chargers.
voltage, low DC voltage and low actually DC power circuitry, right? So they are very good and less costly because of the absence of transformer. I told you the solution, and cheaper also, and you can port it anywhere, take it with you anywhere, right? So that's why it is very popular in these kind of electronic appliances. But now tell me one thing. Let us analyze it further, right? So you understood the operation. So let's dive deeper, okay? So let us draw the waveform. So if your input voltage looks like this, tell me what your output voltage will look like. Let us analyze. So this is the input voltage, right? So this is the positive low. I am assuming nothing is positive, nothing is negative. Just I am assuming this is the positive, this is the negative. Okay, so what is your, tell me, what is the operation? Tell me. When this we what the draw circuit one for
Sir,
your convenience.
so give me diode names, sir.
Yes. I will give you that. Just hold on. I want all of you to participate, okay? Because mugging up will not help actually. Because I can just flip the network. I can just flip the network means what I can do, in the exam.
Yes, sir.
If you mug up the diode names, I can play. What I can do, I
Only
can
diode.
plug the AC supply here and I can plug the load here.
Okay, sir.
And in the assignment, what I can do, I can plug the AC supply here and the load here. Then you will be lost. Or what I can do, I can name this D1, D2, D3, D4. And in the exam, I can make D1, D2, D3 and D4. Then you will be completely lost if you don't understand the operation properly. So don't mug up the diode names. That will not help. I can guarantee. So now looking at this illustration, you tell me, refer this, okay? Don't refer this. So looking at this illustration, can you tell me what will happen if I impress these kind of voltages? That means this lead is positive.
Diode D3.
In the positive side.
Yes. Diode D3 and Diode D3,
Correct.
diode D3, diode D4 are forward biasing, sir.
Why? Because this voltage is higher. This
Higher.
voltage is higher polar, right? And this
Anode is
voltage,
a higher potential than cathode.
yes, correct. So that's why all of you, I hope, are understanding what I'm trying to tell. The diode is always forward bias when this anode is getting higher voltages, right? So this diode here, D1 and D2 will try to get forward biased. And what will happen? I am drawing with another color. So your supply has a positive polarity now. So what will happen?
The
This
current flows.
diode,
The current
no,
flows.
no. First a link will be created. Don't jump. First a link will be created from supply to load, right? So load will get a link with the supply because these two diodes are enabling the
Short
link.
circuited.
This will enable the link of the load with the supply. So this kind of connection will be formed, and accordingly, if it gets a resistance, then this complete voltage is impressed across the resistor. So is it a linear or a non-linear?
Linear. Resistor is linear, sir.
This kind of waveform will be linear only. Or else I can tell a diode bridge rectifier plus resistive load single phase. Okay, so someone is telling the screen is not visible. Are you able to hear my voice?
Visible, sir. Your screen visible. Your voice also audible. No
Okay,
problem.
so just I request you to kindly disconnect once and then get connected once, because maybe the net issue, the screen not loads. So the screen does not load maybe because of the network issue sometimes. So just disconnect once and then reconnect with the link, and then you can see the screen. So what I'm trying to tell, the diode bridge rectifier plus ARD load single phase, okay? Please note this is single phase. Is a linear load. Is a linear load, okay? Is a linear load. Why linear load? Because the current, how it will flow? The current will flow like this. And what will be its
Not.
share? What you are telling? Someone is telling something.
No, sir.
Okay. So what I am
Someone
trying to tell,
audio.
the current will be what? V by R. Simply V by R, right? And in phase, because V by R only, right? So now tell me what will be the, so I am drawing the current, right? IG. Okay? IG or something you name it. Maybe I try to tell it IG only. VG IG, okay? Or V in, whatever you name. So,
IL. IL.
yes. I load or IG, because both will be same. Or not. IG and IL will be same or not. So IL and VL also I will draw for you. VL is load voltage, that is voltage impressed across the 2 points of the load, and the load current. So let us see whether IL and IG will be same or not. So what will IL look like? So IL, I have to assume one direction, right? So let us assume this direction as IL. Or maybe this direction as IL. Just for convenience.
Right to
Okay.
left.
Correct. Let us assume, okay, this direction is IL. So now what am I seeing? My IG. So this I am drawing with other color, okay, because otherwise you all will get confused. So I am drawing IG here, IL here, and VL here, right? Now let us again change the color. So what will it look like? IG. Tell me IG first. In the positive half cycle, IG will be also in line with your voltage V by R. Up to this it is clear.
Clear.
Then what will IL look like? Same as
Same.
IG. Okay, that is also good. Same, V by R is the V by R. Now what is VL? Same as VG. Let us draw with other color. V. VL is V, right? What I assumed VL? This. This I assumed as VL. I name this variable as VL, right? Load voltage. So now tell me, in the negative half cycle, what will happen?
So
D2.
diode D1, D2 are forward bias.
Now it will
D3,
flip.
D4 are reverse bias.
So now it will flip, and these two diodes will be now reversed bias. And then these two diodes, D1,
Diode,
what
diode
will
D3, D4 are open circuited, sir.
and D2 and D1 are forward biased. So if D
Forward bias and short circuited.
so D in this zone, sorry, I wrote it D1, D2, it will be D3, D4. Okay, D3, D4. D3, D4 were conducting. And here D1, D2 will be conducting. Because now the polarity has changed, right? So D1 and D2 are forward biased.
Now
Once D1, once
current.
so D1 and D2, if it is forward biased, then how will it look like? Maybe some color. Yes, let us see. So now D1 and D2 are forward biased. So the link will be formed how? How the link will form?
So now the current is flows from diode D to anode to cathode, sir.
So let me draw here. Okay. So what will happen here? Up to this, there is a link. Now this diode will form a link.
No, sir. No direction, sir. From
What?
sir, here current is not flows from anode to cathodes.
No. I am trying to draw the connection link.
Okay, sir.
Once the diode is forward biased, it will by a wire. Draw the link.
Okay,
There
sir.
is a resistance.
Sir, your
Then
voice
there is a
not audible,
diode
sir.
sitting. Audible?
Now, okay, sir.
So what I am trying to tell, there is a diode sitting here which is forward bias, D2. Then here is I can replace by a short. Then this wire, then this wire, and then this wire. So like this, the current can flow. But the supply is now also reversed. Like this. Right? So the current will flow like this. In this direction. Right? Current has reversed because the supply has also reversed. So IG has reversed. Correct? Up to this it is understood, right? Because IG was assumed to be in this direction, but now IG is flowing due to the reversal of the polarity of the supply. IG is now also reversed. So it is minus. But how is IL? How is IL?
IL flows through diode D2.
No, okay, D2, but how is the direction? Has it reversed or not?
Sir.
No, right? IL has not reversed. Just check. IL is still in the same direction, which is from right to left. IL is still in the same direction. However, IG has reversed. Do you note? So IG has reversed, but IL has not reversed. So IL is still like this. And how is VL? VL has also not reversed. It is a very good point to note. VL has also not reversed, right? Just check. VL has assumed and supply has create voltage across the load has not changed the polarity. Neither the current to the load has changed its polarity, although the supply has changed the polarity. For which the supply polarity has changed. As you can see in the negative half cycle, the supply current polarity has also changed, but the load polarity, voltage and current both remains in the same direction or same polarity, you can tell. So that is the beauty of the full wave bridge rectifier, and the operation ends. So now the operation will continue like this. And you get a toggling voltage and a toggling current, which is DC but with ripple. So do I like this? Do I like this? Your bulb will once glow and then dim. Then again it will glow and try to dim. Do you like this? Obviously, if your supply frequency is too high, then you cannot see the glow and dim. And the bulb will almost either remain completely dim or completely glow. But we don't want these kind of voltages because there is lot of ripple. We want a fixed DC voltage, so we go to the bridge capacity. So the question is, if I call this V rectifier or VL, whatever you tell, how will it look like? So how will the V rectifier, or you can tell V load, will look like? Because load is connected like this, same circuit, okay? No difference. Previous circuit and this circuit, no difference. Only what difference? A capacitor is connected in parallel.
Capacitor is
The ripple.
connected in parallel to load.
Otherwise, no difference, because you can see here across these 2 points, I connected the resistor initially. Now in this circuit only I connected a capacitor in parallel. Only this much change I have done. But what I am asking you is how the V rectifier will look like. Because of the difference in the charging and discharging paths, will there be any difference? Can you just guess? Now what will happen with the diodes? Can anyone tell me? How will the circuit behave now?
Sir, load voltage maximum value will depend upon the capacity of capacitor.
Correct. Is this voltage, full, this node voltage, right? This, if it volt, whatever is the load voltage, I can tell. If it is lower, rather the time it is lower in the supply, then it will work. However, if the load voltage is high, because of the discharge path is actually increasing. The capacitor is holding the voltage, right? If the higher value of capacitor you use, then it will not allow this voltage to drop easily. So it is creating a barrier between the supply and the load. It is not letting the load voltage fall. The supply voltage is rising, then falling like this. But the capacitor is not allowing that to happen. So what happens? There is a kind of difference between the load and the supply. It is not following it completely. So what happens in this point? If the voltage is high, and at this point or the supply point, the voltage is low, then it will come down. And capacity will not, because the capacity voltage allow the voltage to fall easily because it's like okay. But the time charging during the charging, but it's not the distance. Again, coming from you, some voice. I can mute also from here. So what I am telling, due to the difference in charging and discharging path time constants, there is a asymmetry in the charge between the, I can say, input and load. They are not following each other like the initial part. They are constantly following each other, but here they are not following. So what will happen? Let us draw. Initially the capacitor was not charged, so 0 voltage. So what happened in the positive half cycle? These diodes, these two diodes, D1 and D2, as you can understand, got forward bias. D1, D2 got forward bias because this voltage was 0 volt initially. So forward bias. D1 and D2 got forward bias. So as soon as D1 and D2 got forward bias, they just allowed the voltage to appear across the load by creating the link, and the voltage appeared. But will it appear completely? Will it actually fall like this? The supply voltage is
No,
actually falling.
no,
But
sir.
will this, so tell me then how much time will the diodes remain forward biased? Up to the time I told you this voltage,
Input voltage is greater than capacitor voltage. Up
up to the time input voltage is greater than VL, I can tell capacitor voltage or VL. To the time VI is greater than follow the waveform. But now at this point, after this peak, your V supply is lesser or V input is lesser than VC. Why? Because capacitor voltage is actually trying to maintain this voltage. Okay.
capacitor voltage charged to peak, sir.
Charge to peak, and it is not easily allowing to discharge the voltage, for which the diode is getting reverse bias. So after this point, diodes reverse bias. Diode got reverse bias midway.
Diode not reverse bias, sir. Voltage, input voltage reduces, sir, after this peak.
No, diode reverse biased only.
Okay.
Diode reverse bias. Just check, okay? Just check and think. Diode reverse bias, okay? No issue with that. And at the very starting, this part, diode will be diode D1, D2 will allow capacitor to charge by forward bias, right? But what will happen? After this, once the capacitor got charged, it will not be so easy because of this rule. As for the next cycle, I am not drawing what will happen here. Forget about it. But for this part, okay, for this part, similar part, here also the diode will be reverse biased up to a time very close to the peak when this capacitor will discharge before that, because the diodes are reverse biased. Why reverse biased? Because input voltage is still lesser than the capacitor voltage. Capacitor voltage is large. Capacitor is large. Assume
Now the capacitor discharging to load resistor.
Capacitor is like that. It is not allowing the voltage to fall. But when the supply very much reaches close to the peak value of the supply, then it will slightly get higher than the capacitor, and then the diode will be forward biased only for a small time in this zone. But in this first time it was forward, some current flow, V by R current flow, but up to this point. But here a peaky current will flow and go down. Similarly, what will happen here? Tell me. So this is IL, right?
Capacity discharging to load resistors.
No, not completely. There will be a time when the supply voltage, the rule is like this.
Yes, sir.
When the input will cross the capacitor voltage, then so capacitor voltage was slowly decreasing after the diodes were off. No diode was conducting in this zone. No diode conducting. So the capacitor was slowly discharging. And then input voltage become like this. Input voltage flip, just for reference. Then in this part, the input voltage surpassed the supply. In the negative you think, because I told you, the capacity in the negative cycle also, the voltage across load does not change polarity. The load will see this voltage only. But will it be able to get that voltage? Only when the diodes are creating the link between the supply and the load. Only when the supply surpasses the capacitor voltage. Capacitor was slowly trying to decrease like this. And the supply was trying to increase. At that point, the diode will again get forward biased. That will happen for a very small moment. So load current will again be in the same direction, and voltage polarity across the load voltage polarity will still be same in the positive half. But the grid voltage or whatever you source voltage, you source current and voltage will flip the polarities. So Ig polarity will be like this. Okay, this is the waveform of Ig. This will be the waveform of Ig. And as you can understand, it will happen very before the peak, slightly before the peak. Slightly before the peak, it will happen. Up to the peak and slightly, the notch will actually happen before the peak, right? And then it will just go away. Because by then the capacitor will start to again fall. So this is the waveform. Actually, peaky shape currents for very small duration will flow. And if you try to draw the fundamental of this, then you can see that this circuit is creating a leading power factor current here at the supply. So just remember, just you can draw in the FFT and see that the spectrum actually, and see the fundamental by filtering this waveform. The peak of the supply and the peak of the current, you can see the peak of the fundamental of this waveform will slightly lead the peak of the fundamental of the, because of one simple reason, that the difference in charging path and discharging path time constants. The capacitor is have a larger time constant. However, the forward bias time constant is very small. Immediately it is getting forward bias. So that if you draw the overall sign fundamental, then it will slightly lead. And that is very obvious because of the presence of capacitor. It is creating a leading power factor effect on the supply. So just remember this. And as you keep on increasing this capacitor, many increase the size. That is what I want to say. That is the capacitive reactance you are trying to actually reduce. So the capacitance effect is enhanced in the current, right? So basically, if you increase the capacitance value, it will create more and more leading power factor effects. The power factor is very poor actually. I am talking about displacement power factor, DPF into DF. Distortion factor is nothing but power factor. Overall power factor 0.55. But the displacement power factor is leading in nature. The fundamental, the phase shift is kind of leading in nature, okay? Slightly, if you see. And the more notchy it becomes, because of the more value of capacitor you add as a filter, the more it creates the leading. More leading it will become, the sign. Because whenever more notchy waveform will come, it will shift the peak of the sign to the left. Just check it, okay? You can understand once you do it yourself. Because otherwise, if you don't see the spectrum properly of the fundamental and then draw the fundamental, how the peak is shifting, you will not understand. But it is happening like this, okay? So hope this creates a very small introduction like this, because this is basic course, Introduction to Electrical Engineering, but in power electronics, this is helpful, right? To see how the power factor and all will, for persons who do PFC and all those research. In research areas, it is very much useful to have this kind of application based information, because you need to actually control the power factor, to be control the current waveform, to actually become in line with the voltage waveform, to actually improve the power factor of the circuit. So there are techniques by using front end converters and all those things, but there you need this waveform knowledge. So hope this is a very small actually thing. So we are already late. Let us first cover the peak inverse voltage across each diode, just for your practice. This is just 440. So what is the secondary voltage? 440 by 10. It is V secondary. Now V secondary RMS. Now I told you this voltage will be V secondary volts. And what is the V secondary by 2? What is the
So root 2 into 88 peak
voltage?
inverse voltage.
Root 2 into 22. And then you can understand that peak inverse voltage is nothing but 2 times root 2 of 22. Or nothing but the peak of the secondary voltage. V secondary peak. It is nothing but 44 root 2. Because V secondary was nothing but 44. So that peak will nothing but the peak inverse voltage that the diode has to block. So understood, right? It was easy. Now I want you to calculate average and RMS, which we already did in the week 2. Just go back and check the half wave and full wave rectified DC voltage, average and RMS, like this. Sorry.
Sir, can you go for previous question, sir? I have small doubt. Sir, here peak inverse voltage is nothing but 2 into V.
This voltage. 2 into this voltage peak.
Sir, okay, sir. Got it.
But in other words, V secondary peak. Because this voltage is itself half of the V secondary. Okay?
Got it, sir. Got it,
It's
sir.
easy. If you see once, you will understand. Okay, easy. So this is half wave voltage and this is full wave rectified voltage. Okay. So we determined the RMS value and average value. RMS value was nothing but peak by root 2. And here the RMS value was 1/2.
Vm by 1/2.
So just check again. Okay. Just check once again. You will understand what I am trying to tell. And average of a sine is 0. But average of this?
Vm by root. Average of
No.
this one. 2 Vm by pi.
2 V peak by pi and this will be V peak by pi. These are all average, right? What I am trying to tell. And this is V peak. And V peak is nothing but root 2 times VRMS. Hope you understand. So check derivation in week 2. Where we solved the average and RMS, right? Of many waveforms we did. So this is easy. So now just a very popular problem. Just see the problem and then I will tell you what to do. I will tell me first. Yes, am I audible?
You are audible, sir. Audible.
What I am trying to tell, these kind of problems are usually given. Some kind of non-idealities or is added. So, but the problem still remains the same, right? What is happening? This is a full bridge rectifier. So, what is the what you know in each and every cycle, positive or negative, how many diodes conduct? 2, right? 2 together, always. In every cycle, always two diodes will conduct in pair. Here also 2 diodes conduct. Here also 2 diodes conduct. So at a time, how much drop will you face?
1 volt.
2 times this much drop. So if the sign was like this and I just eliminate a 1 volt from the peak, because average voltage was 2 V peak by pi. Now Vm will be, initially Vm was 10 root 2. Now, but V peak after drop will be?
9 root.
No, not 9 root 2. 10 root 2 minus 1.
Okay.
So average 2 by pi times 10 root 2 minus 1. Do it and see how much it is coming. And then your I average will be, because there will be repel, so we are talking about the average, right? So nothing but
8.36 volts.
so it is 1 ohm, right? Okay. So this is nothing. So what is it coming?
8.36. 8.36.
Whatever, 8.36 volt and 8.36 ampere, right? Because RL is 1 ohm. So let me check whether we have done everything correctly. 10 root 2 minus 1. 8.367, so it is okay. Yes, this is the correct answer. Okay, so basic problem, only consider the drop for the V peak, because there is 2 diodes conducting and that information was necessary. After that it was same. Just the average and I average. Just apply the V by So are you able to see the screen?
Yes, sir. Yes.
So just let us start the two-port networks. Okay. So basically the introduction of the two-port network, what you understand? We have a port which we call the input port and the output port, right? Okay. So can you just okay. So I ask to mute because some sound is coming from your end and it will disturb the recording actually. So just unmute if you have something to tell. So what I want to tell, maybe the two-port network is a mathematical simplification which we do for the electrical network in order to simplify the calculations. And while networks. So those larger networks can be further simplified. The overall network can be broken down into sub-networks and representation can be done using this two-port network so that it can encode the overall system within as a black box which has some parameters which we denote as some. We'll just talk about the parameters and those parameters will define the network. We don't need to actually deal with the complete network, and there are some simplification tools which mathematically makes the system equivalent to the overall system. But this network actually is a input output based network, and this input output based network which deals with a electrical system is a mathematical simplification for dealing with complex networks. So mathematical understood or no? Just you can unmute and tell me. Yes, you can unmute. Understood? Is a mathematical simplification for complex networks. And as you know, in electrical networks, if the input current is coming in this way, the output current is like this. Maybe let us assume, but the same current should return also. So it's a single entry point network, and the single puller
Sir,
three-port electronic network.
sir, your voice struck, sir. Sir, your voice not audible, sir.
Here, I can just check here in my mobile. I think your network now is having some issue. Now voice is clear, I think. So it is a mathematical tool to convert three-port electronic networks in form of two-port electrical networks, so that we can interface both and deal with complex calculations and complex systems, right? So basically it is a mathematically simplification tool, and obviously there are ten clear? My voice is clear now? Screen is visible? You can unmute and just tell me if you face some issues.
Screen is visible, sir.
Voice clear, right?
Okay.
Voice clear? Able to hear me correctly?
Clear, sir. Clear. Now clear, sir.
Okay. So just was dealing with some two-port networks, how they are dealt with, and as you can understand, it is a single entry and single output point for the network to deal with dependent and independent parameters. Now, obviously, there are dependent parameters and independent parameters. What you understand by independent parameters? The parameters which we have control over are obviously independent parameters because they do not depend on anything, like the forcing function or the supply voltage. We can control it. And the response of the network as a result of that supply voltage can be dealt as a dependent parameter. It depends on the use of the network and the selection of the parameters. Now we have several parameters for several purposes. For dealing with several same network having different parameters. Why? Different forms of representation, I can say. Why so? Because such representation simplifies the mathematical calculation in several different applications. Because this may be a subnetwork. Now, if such subnetworks whose parameters you know, some parameters you know, such parameters of other subnetworks also you know, maybe connecting these two subnetworks in series, knowing those parameters can simplify your analysis and help you know the complete system. And even if they are connected in parallel, then that may also help. A different parameter may help you in that case to know the overall system in that terms of parameter. Now, going from one parameter to another parameter is very easy because if you know the dependent and independent variables, you can just switch one to equation. For example, if you know x as a function of y, z, then you can immediately determine z as a function of x and y. Like that. You can toggle around and just select the parameters as per your convenience during different situations. Depends on how subnetworks are connected will declare selection of parameters. Now, as you can understand, there are input and output parameters. Input voltage, input current, output voltage, output current. So there are 4 parameters. Two-port networks from input and output forming the 4 variables. Now, out of these, 2 are dependent and 2 are independent. Let us assume. Then how many combinations? Can anyone tell me? How many permutation and combination can you do? 4C2. Out of 4, 2 you have to select. So that means it is 4 factorial by 2 factorial, 2 factorial, right? Which is nothing but 6. So 6 parameters are possible. And the name of 6 parameters are Z, Y, T or ABCD, H, ABCD inverse or H inverse or G. These are the 6 parameters. They are nothing but the different representation of the same network. And you get different matrices. So they are nothing but different representation of same network. Using different input and output variables. Understand, right? Y, this you call as the impedance parameter, this or the Z parameter. This is the admittance. So always remember Z parameter. So Z parameter are useful for series connected subnetworks, series input, series output, and these are helpful for parallel because you know admittance adds up in parallel because the current just sums up. And then the impedance parameter is useful for series connected networks because that also is easy to add, and the overall so kind of applications help to determine actually. So basically Z and Y parameter I will write down. If you have a black box and then you have the V and I, V2 and I2 is always into the network, right? It is a convention, except ABCD. Except ABCD, parameter, I is we tell you why for ABCD down the Y parameter that also such specific representation wise. So as you know, V equal to I into Z.
Sir, not audible, sir.
Audible?
Now, okay, okay, sir.
Huh. Sorry. So as you can see, I will write once again. So V, which is nothing but a 2 cross 1 matrix, is nothing but a 2 cross 2 matrix times a 2 cross 1 matrix, which is nothing but I into Z. You can because there are two one is nothing but Z11, Z12, Z21, Z22 into I1, I2. And the Y parameter representation is also very easy. And for symmetry, Z11 equal to Z22 for symmetry. Obviously, as you can understand, because V1 by I1 should be equal to V2 by I2. For symmetrical input output, right? So that's why from there you get this result. And obviously you know reciprocity. For reciprocity. Reciprocity means that you can just interchange. Okay. And it will not affect. So another dual I can say is I equal to Y into
Y into V, sir.
So that will also give similar result. Basically, Z matrix inverse is nothing but Y. And matrix inverse is nothing but 1 by adjoint of that matrix into the co-matrix, that transpose. That you know already. So here I can say V1 and V2 are the dependent parameters and these are the independent parameters. Similarly, I can say here I is the dependent parameter and V is the independent parameter. So as you can understand, what will be the law of reciprocity? Similarly, y12 equal to y21 for reciprocity. And for symmetry, y11 equal to y22. Clear? Going to the ABCD parameter, it is interesting. Now ABCD parameter is actually built on the virtue of some specified application in power, where we have our home, right, and we have a generating station or power plant. Now we have the transmission line in between, right? So that transmission line model can be encoded using, it is very easy, using ABCD parameters. Why? Because there we have the independent variable as the home loads, VL, IL or V2, I2. These are the independent. Because this you don't have any control upon. Load, you cannot go to the user and ask that, yes, you give me or you please take 1 kilowatt power and don't take more than that. You cannot tell a user like that. So these are the independent parameters at the output side, and the current will be out of the box. So that's why the current direction in ABCD is always out of the box. Please remember that, it is important. So that builds up the network for the ABCD. So ABCD is basic, but here you have V1, you have I1 into, because the current from the generating station, and the output also current like this. So this is a convention. Just you have to just simply assume I2 in that direction to be positive, and accordingly determine the ABCD parameter. So this is A, B, C, and D. And how it is denoted? V1, I1. So as you can understand, I told you these are the independent variables. I told you here. So basically they will form the ABCD parameter. Just different representation of the same network. And minus I2. Why? Because I2 in this direction is taken as positive. But in two-port networks, I told you, I take currents going into the terminal. So minus I2, that's why. To simplify and harmonize all the parameters. Not make the parameters negative itself. I do like this. Okay. And otherwise, law of reciprocity and all I will tell you. So law of reciprocity tells that AD minus BC should be 1. And your symmetry is A equal to D. This is symmetry. So by identifying A equal to D, you can say that the network is symmetric. That the network is reciprocal or not. And same by the H parameters, which is useful for. So the ABCD was useful for transmission lines. Similarly, H parameter was very useful for dealing with analog networks, 3-port analog networks. So that is easy to determine the 2-port equivalent electrical form by representing with H parameter, right? You can correlate 2 parameters at once and then see the effect on other 2 parameters. 2 dependent and 2 independent. That is the whole point of 2-port, right? So here also you can say that this is V2 and this is I. Clear, right? Okay. So just the denotion of the each parameter, how to denote it. So each parameter you can just determine as V1 I2, and it will come as H11, H12, H21, H22, and then you have I1 and V2. And the reciprocity says that H12 should be equal to minus H21 for reciprocity, and H11, H22 minus H12, H21 should be equal to 1 for the network to be symmetric. Now I will give you some relation of H parameter with ABCD and ABCD with Y and Z, right? Correlating all. So as you can understand, H11 is nothing but V1 by I1, keeping V2 0. H12 is nothing but, and also Y11 is nothing but I1 by V1. So what you can say, keeping V2 equal to 0. And Y21 is nothing but I2 by V1, keeping V2 as 0. And H21 is nothing but I2 by I1, keeping V2 as 0. How I am keeping? Just seeing this network. You see H11, H21, H21 is this. So H21 is what? I2 by I1, keeping V2 as 0. You can just see from this network. And then the relation, just equalizing this 4 relation, we get 1 by Y11. As you can see, H21 is also Y21 by Y11, and Y11 equal to 1 by H11, and Y21 equal to H21 by H11. H22 again is nothing but I2 by V2, and I1 is 0. Similarly, Z22 correlating with Z is nothing but V2 by I2, I1 as 0. Now I can correlate by the inverse. So what it gives me? H22 it gives me is 1 by Z22. Similarly, H12 it gives me is Z12 by Z2. You can just correlate from here. And then I get Z22 as 1 by H22 and Z12 as H12 by H22. Now you know Y is Z inverse, right? And Z is nothing but Y inverse. So correlation among them was very easy. Now correlating H parameter with Y and Z, and now also correlating ABCD parameter with Y and Z, right? So what ABCD parameter, how can you correlate? A, B, C, D, right? Here. So A is what? A is nothing but V1 by V2, keeping I2 0. Just see this equation, okay? And what was C? I2 by V2, keeping I2 as 0. Then what is Z11? V1 by I1, keeping I2 as 0. And Z21 is nothing but V2 by I1, keeping I2 as 0. So what can I write? A and Z11 and Z21. It is nothing but the division of the two. So A is nothing but Z11 by Z21. And C is nothing but I1 by V2. Just see this. I1 by V2, keeping my I2 as 0. Then C becomes equal to 1 by Z21. So these are the two relations that we got. Similarly, by seeing the network, you can understand D you can write as this and B you can write as this. Then you can understand from this. Okay. So these 4 relations correlates ABCD, Z parameter, Y parameter, and the 3 already so correlated. And then a final parameter, you say G parameter is nothing but H inverse. G is nothing but H inverse. And ABCD inverse parameter also exists. But that will not be helpful in many places, but they are useful in some places. So I will tell you at the end where they are used. Any doubt up to that? It is only representation, just matrices. So one simple problem, let us see that how to deal with H parameters, right? So are you ready to solve the problem? This is one problem. Are you with me?
Sir, I am there, sir.
So find the H parameter for this problem. So H parameter is what? Let me again write for you.
V1 I2.
V1 I2.
H11 equal.
So find this network. You have to find the H parameter, right? Yeah, H parameter, okay? So what will be the approach? Our approach will always be to convert V1 in terms of I1 and V2, write down the equation, and to convert I2 in terms of I1 and V2. Okay? That will be the approach. So try. I will give you 1-2 minutes. So what can I write here? This is 3I1, right? So what is this current? If this is 3I1, this is 3I1.
3I1.
3I1 plus I2 by KCL.
Yes, sir. Got it, sir.
Here.
Entering current I1.
Out of 3I1
I1
plus I2, 3I1 already went away. So I2 will go here.
I2 is going to 1 ohm resistor, sir.
Correct. So out of 3I1 plus I2 and also incoming I1, let's apply KCL. 3I1 already went away. So the current to 1 ohm is nothing but I1 plus I2. I1 ohm, right?
Sir, yes, sir. Got it, sir.
So once you got it, it is over. V1 is 1 into I1 plus I2. And then write about V2 and I2. Two equations you need, right? One more equation you need. Apply KVL in this loop.
Yes, sir.
So V2
minus V2
3I1 plus I2 into 1.
3I1 plus I2 plus 1 into I1 plus I2.
Minus I1 plus I2 into 1. These are the drops, right? See from here. Equal to 0. V2 is nothing but
V2
3I1 plus I2 plus I1 plus I2.
for V2 equal to 4I1 plus 2I2.
But what we need V1 as a function of I1 and I1 and V2, and I2 as a function of I1 and V2.
H11.
No, forget about H.
Okay.
That will come at last.
Got it, sir. Okay, sir.
You try first to determine V1 as a function of I1 and V2. We have V1 as a function of I1 and I2. I need to replace this I2 as a function of
V2 and I1.
And I1. So you see 2I2 is V2 minus 4I1, right?
Yes, sir. V2 minus 4I1.
So now as a result, I2 is coming half of V2 minus 2 of I1. This you can plug in here. to get V1 as a function of I2, I1 and V2.
I1.
So I2 you replace half V2 minus 2I1, which is nothing but half V2 minus I1. So the first row is done. Half and minus 1. Sorry, minus 1 and half, right? Because I1 is there, right? So minus 1 and half. And the second row is done already as a function of V2 and I1. I1 and V2, sorry. So minus 2 and half. So is the network symmetrical and reciprocal? What was the law to check for each parameter? H12 should be equal to minus H21. So no, right?
Yes,
and
not
for symmetry, H11, H22 minus H12. So minus half times minus 1. No, right? Not symmetrical. So neither symmetrical nor reciprocal. So that's how you deal with such problems. And this is an easy problem. Find all parameters for network. I will write down the answer for you. Do that work. Try it at home. Try to determine the Z, Y, and CD parameter as well as H parameter. Right. So I'll write down for you the answer. Simple like this. Okay. So I'll write for you the answer. Just check at home. So the Z will be, I think, 5, 3, 3, 5. And the Y will be this much. So note the problem and then write down the results. Because I hope you will be able to solve. It is only a game of changing the equations, changing the variables and then seeing the matrix. So ABCD is nothing but I am getting 5 by 3, 16 by 3, and then 1 by 3 and 5 by 3. And also inverse ABCD, right? Saying 5 by 3, 16 by 3, 1 by 3 and 5 by 3. And H and inverse H. So H will be 16 by 5, 3 by 5 and minus 3 by 5 and 1 by 5. And H inverse or G matrix, you also write here, is 1 by 5, 3 by 5 with a minus sign, and then 3 by 5 and then 16 by 5. So just solve and check yourself. And let me know if any doubt.
Okay.
Because I hope you can solve this. Just take a screenshot or maybe just copy. I will wait for you. Taken?
Yes, sir.
So I just remove the remaining pages because you can solve it by yourself as a homework. So this would be leading, right? This I already discussed with you. That the power factor will be leading. So just that much was there. Other than that, yes, a very important thing. I'll take 5 minutes. How to actually utilize these parameters. For what purpose they were actually designed. I told you they were designed to deal with subnetworks and simplify very complicated networks by encoding the complete subnetwork information within the parameter blocks. Now their actual roles play or manifests their role when the network is actually encoded through some series and parallel interconnections. Then you can see what their importance are actually. And different parameters have different importance in different connection networks. Like for example, if you have input series and output series, then always your Z parameter will help you, as you know. If you have input parallel, output parallel, both, then your Y parameter will help you. If you have cascade, I showed you what cascade means, then your T parameter or ABCD parameter will help. But help how? The equivalent ABCD parameter will be product of the ABCD parameter of the two subnetworks. Remember, product. Just check, it will work. You can just derive. It is very easy to derive. You can write the for one, write for two, and then write for the overall. You can see that it will hold true. And input series, output series, you can see first one, series in, series out, I have showed you. You can also derive that V11 plus V21, or I can write V1 plus V1 prime equal to V1, or V1 prime plus V1 double prime equal to V1. Just input side. And this you have already known the Z parameters. So just check, it will just commuted to form the Z total is not of this network. If connected in series and series at both input and output, will just sum up to the indicators of the two series connected networks. And each parameter is like this. So at different connection ends, different parameters are helping you to associate and form the or give you information about the final overall complicated network. So without solving many loops and without solving many nodes, you can directly claim or directly give information about the input output relation of this complicated network by using the interconnection principle and using the different sets of parameters for different systems with different interconnections. Understood? So just take down this and just try to check and derive if these holds true. Just cross check to gain insights. These are always obviously true, but you should derive yourself. Take any two subnetworks and try to connect them in series and parallel and series and series and series and maybe parallel and parallel and cascade, and then series parallel and parallel series to check if these relations hold true or not. So G, as you can understand, is nothing but H inverse, and T is nothing but ABCD, right? So just check. Okay. And with this knowledge, I want to show you one very simple network. Not very simple, but it becomes simple if you reduce it and try to solve it piece by piece as subnetworks. So see this problem. This is the final problem of today's session. And I hope after solving this problem, you will be able to solve all the two-port network problems. Because you now know how to deal with subnetworks. And you now can use different parameters to solve complicated networks by simply series parallel laws, right? How to derive different networks for the two networks, subnetworks, and then interconnect them to form the overall network parameter. So just try to derive the Z, and by just looking the term Z, you try to reduce as two subnetworks which are what?
Single network.
Single networks, but input series and output series both. right? Which are two subnetworks, like two port should be, their output should be connected in series like this. Two subnetworks, but their input should be series connected and output should be series connected. Can you reduce this network to this?
Yes, sir.
How? It is not properly series connected. I cannot see any series connection.
Sir,
That I can...
one is delta connection, another one is star connection, sir.
Correct. So what you will do? Convert this delta to star.
Delta to star.
Correct. And this node remains the same node without changing the network properties. So this value will be 20 into 10 by 20 plus 10 plus 60. You know the law, right? Then this into this by sum of the three. 60 into 20 by 60 plus 20 plus 10. And the final one is nothing but
60 into 10 divided by 90.
Then you just see, then these two will be series connected. This dot and this dot will now come in series. So you first determine, you draw a line here. You first determine the Z parameter for this network by telling it V1, V2 between this node, right? And I1, I2. I am drawing again, okay?
Yes, sir. Simplified values.
So simplify it.
60 into 20.
I will write for you, okay?
Sir, one is 13.33 ohms.
I will write for you. So how it looks, first see.
Star.
And these points are unperturbed. Now this point was connected to this point. Which was 50 ohm, 10 ohm. And your this will be
40.
1 second. Just let me check. This is 40 by 3, 20 by 9, and 20 by 3, right?
6.66, 20 by 3.
So what you can do, you can break this and this. This becomes one subnetwork. Then break between this and this and this.
What about 40 ohm resistor, sir?
Where is 40 ohm resistor? 40 ohm is there, na? Sorry. Fortium is also connected like this. So this is correct, right? This is connected in series. So basically what I mean to say, this network is output series and this network is also series connected. Agree or no? If I can find the network parameter, Z parameter for the upper one and this parameter, then what it looks from outside, that your this wire, and if I take this wire, okay, just fictitiously, and I take this wire and I take this wire, okay, and I then outside it will just go to the 10 ohm. So discretely you just consider this one as another, because this also is series connected. Okay, from this is connected, right, with the upper one. The upper one, bottom leg, is then series connected with the lower one. So this up to this, only this. This is the lower one and this is the upper one. Individually you determine these two Z parameters. Maybe Z prime and Z double. And then the overall network is series connection version of 2. Yes or no?
Sir.
So overall Z equal to Z prime plus Z double prime. Simple, right? Break the network into two other networks and then find the Z parameter of them separately. And then the actual network is a series connected output version of the old ones or the sub network ones. You add the two and then get the overall Z parameter. Because that is what is required. Okay. So I will write you the Z prime, Z double prime, and Z. Right. So it will become your Z prime on top
20 by 3.
And then this will become
60, 50, 50, 90.
Yes. That you can also see, right, from here. I1 plus I2. Right. Then 60. Then this one. V1 with I2. Right. 60, 50 you can just see. And then 50 and 90.
80.
And then what will be the two? This one will sum up, right?
80.
80, 170 by 3, 170 by 3. So as you can understand, yes. Yes, there you go. So the rule was to determine individually for two subnetworks. For two subnetworks, and actual is a input output series version of two subnetworks. Okay. So I hope now it will be clear. If you find it to be parallelly connected, input parallel, output parallel, then break the two into two different subnetworks, determine individual Y parameters and add. You will get the overall Y parameter, not the Z parameter in that case. Here you are getting overall Z parameter. If someone asks you, tell me the Y. Z inverse. So don't forget you are getting also Z parameter by adding in case of series input output. But if someone asks you Y, here only, but doing the series was easy, then do everything in Z, because doing the series was easy. Then go back to Y by doing Z inverse. So that is a technique you can apply. Okay. So that was it. You can copy and then we can just close the session if you don't have any doubts.
Sir, one doubt, sir. Why, sir, we are calculating Z dash, Z double dash? Directly we calculated Z in this circuit.
Yes, obviously.
10 ohm and 50 ohm are in parallel.
Well, they see, that was not the whole purpose. The whole purpose was if I would have asked you to maybe give some matrices, Z matrices, then what you would have done? Then also you would have reduced, right, the network. Then reducing that may many networks would have been becoming a problem, because what you can have, you have to actually, you have to do the same thing. Okay, you are actually doing the same thing only. You may reduce the network. I understand your point. That's the whole process, right? But
Okay.
this is the not the whole network. Maybe some more complicated network is there.
Okay.
That will help. So that was the whole purpose, was to actually validate this. So whatever you are telling, you can do that and cross check whether it is satisfying. Obviously, you cross checked and found out that it is holding true, right? So only to make you satisfied that this works. That was the whole point. Okay. It was easy. Relatively, it was easy. You can break into star delta and then easily you can find out V1, I1, V1 as a function of I1 and I2, and V2 as a function of I1 and I2, right? Okay. So if don't have any doubt, we can just close the session and I will upload the video. Some interruptions were there. We'll just check and then upload, right? Okay. We can close the session here, right?
Thank you, sir.
Thank you.